Welcome, this is Professor Ridge and today's lesson 5.3, Graphs of Polynomial Functions. And our first learning objective, recognize characteristics of graphs of polynomial functions. Recognizing characteristics of graphs of polynomial functions. Polynomial functions of degree 2 or more have graphs that do not have sharp corners. Recall that these type of graphs are called smooth curves. Polynomial functions also display graphs that have no breaks. So we can draw it, remember, without picking up our pencil. So they're smooth, continuous curves. Curves with no breaks are called continuous. Okay, so again, continuous. Figure 1 shows a graph that represents a polynomial function and a graph that represents a function that is not polynomial. Okay, so this first one, f over here, well, I guess they're both labeled f, but you can see this first graph, it's a smooth, continuous graph. I could draw it without picking up my pen if I was drawing it on paper. Okay, and then the second one, you can see there's a break right here, and we have a jump. So this might be a function that's a piecewise defined function that we've talked about before, where part of it would be a polynomial and then part of it's something else. Okay, so it's not a polynomial function because of the break. Example 1, recognizing polynomial functions. Which of the graphs in figure 2 represent a polynomial function? So remember, we want a smooth, continuous graph. So no sharp turns, no corners, no breaks, smooth, continuous. So you can see this one I can draw again without picking up my pen. So this one, f is a polynomial. This one has the sharp corner, and you should recognize that as absolute value. So that one's not a polynomial. So this one's yes, no. And then h here, again, it's smooth, continuous curve. So that one's yes. And then we got the break on this one, right? So those are, if you have a corner, a sharp turn, if you have a gap, a break, it's not continuous, then we say no, it's not a polynomial. Our next learning objective, use factoring to find zeros of polynomial functions. Example 2, finding the x-intercepts of polynomial function by factoring. So find the x-intercepts of f of x is equal to x to the 6 minus 3x to the 4th plus 2x squared. And this should be hopefully sinking in by now, right? The way we find x-intercepts is you set the function equal to 0. And then with this technique, if it's not factored, we want to factor it. So look for any common factors, factor them out, and then factor any factorable binomials or trinomials using techniques that we've talked about before, or you should have learned in intermediate and beginning algebra. Okay, so our first steps, we're going to set the function equal to 0. Oops, don't forget the square. Okay, so it's set, we've got it equal to 0. And notice all three terms have x in them, so I can factor out an x, and you take the smallest power because that's what's in common to all three terms. So I factor out x squared. Then I divide out x squared from each of these. And we're going to use exponent rules, so when you divide, you subtract the exponents. So that'd be 4. x4 divided by x squared, you go 4 minus 2 is 2. And then x squared divided by x squared is just 1. So that cancels, and you get 1 times 2, which is 2. Okay, now this is it's a trinomial, and then we're going to do that trick. We're just going to make it behave like a quadratic, but it's to the 4th power, but you still have the 3 terms. So you can do that use substitution idea, or I just say, all right, we have x to the 4th, x squared, So I'm just going to do x squared, factors of 2 that add to 3, 2 and 1. This sign goes to the larger factor, so that's negative. That middle sign goes to the larger factor. And when I multiply to get a positive 2, I have to have the same signs. Negative times negative make positive when you're multiplying. Okay, so now we have it factored this far, and then this is okay, it's not a different square, so you can't do anything with that. This one's a difference of squares, so we can do x plus 1, x minus 1. And then we're going to set each factor equal to 0. So x squared equals 0. X squared minus 2 equals 0. X plus 1 equals 0. X minus 1 equals 0. So this one, when we can square root both sides, x gets plus or minus 0, which is just 0. Here we're going to add 2. And then we're going to square root both sides. So we get plus 2 minus 2. I'm sorry, plus the square root of 2 minus square root of 2. And then this one we're going to get negative 1. And this one positive 1. So let's see, find the x-intercepts. So our x-intercepts are 0, 0, square root of 2, 0, negative square root of 2, 0, negative 1, 0, and 1, 0. So we got 5 x-intercepts. Remember, this is degree 6, so we could have got up to 6 x-intercepts. We only got 5. That's because this 0 is what we're going to talk about this a little bit later. This has a multiplicity of 2, so it's 1 x-intercept, but in the factors we had 2 factors for that x-intercept, because x squared is x times x. Okay, if we look at Desmos with that original function, you can see, if I zoom in on it here, we can see the x-intercepts. And if you did square root of 2 on a calculator, you get 1.414. Right? So this is negative 1.414. And then this one would be a positive 1. Okay? So there's your 5, and we're going to learn about this behavior here. See how it came down and that turning point was actually on the x-axis? We'll talk about that again in a little bit later. It's related to that multiplicity, the x squared, multiplicity 2. So we're going to talk about that later in this section. All right, let's move on. Example 3, finding the x-intercepts polynomial function by factoring. So again, we're going to set the function equal to 0 to find the x-intercepts, and then factor. So if you have 4 terms, you want to factor by, well, first let's see if there's any common factors, right? There aren't any. Then I'm going to do the factor by grouping technique. So x squared comes out of the first 2. So you get x minus 5 when you divide it out. And then remember, I want this parenthesis to match. So this is negative x plus 5. So if I factor out a negative 1, it changes both those signs. And then the parentheses match. And I can factor that parenthesis out. And then when I factor that parenthesis out, you have the x squared minus the 1 left over. Again, difference of squares. So hopefully you're starting to catch on to that one. So you square root both, so it'll be x and 1. Because you square root of x squared is x, square root of 1 is 1. And you do a plus 1 and a minus 1. Set each of these equal to 0. and then solve each of these statements separately. So just add 5, and then we get subtract 1, add 1. So our x-intercepts are 5, 0, negative 1, 0, and 1, 0. And let me get Desmos. Okay, so I typed it into Desmos, and you can see, if I zoom in on it, you can see that it crosses at negative 1, 0 for the x-intercepts, 1, 0, and then 5, 0, which is just what we got. All right, okay, moving on. Example 4, finding the y and the x-intercept of a polynomial in factored form. Okay, so we'll start with the easy one, y-intercept. If you recall, the y-intercept, right, that's where it crosses the y-axis, so the x-coordinate is going to be 0, and then we plug 0 in for x and figure out the y-coordinate. So this is g in this case, so it'll be g of 0. So we plug in 0 into the function and find the y-coordinate when x is 0. So 0 minus 2. Oops, that should be 0. So we get negative 2 squared, which is 4. 0 plus 3 is 3, which is 12. So our y-intercept is 0, 12. Now we're going to do the x-intercepts. I'll just write x-int. And again, remember, we're going to let the y equal 0 and solve for the x-coordinate. And we typically use a for x-intercept. All right. So let's see, we're going to put 0 here, or you can switch it around, doesn't matter. Well, the hard part's been done for us since it's already factored equal to 0. And we're going to set each of these factors equal to 0. You don't have to worry about the square, because you would, if you said, here, I'll show you. If I set that equals 0, 2x plus 3 equal to 0, you square root both sides. The square root of, well, I don't need the parentheses. The square root and the square cancel each other, and the square root of 0 plus or minus square root of 0 is just 0. Okay, so basically that square is going to go away, and then you solve this, you add 2 to both sides. And then again, we're going to be talking about multiplicity in a little bit. So since this factor x minus 2 occurred twice, the power 2, we would say this has a multiplicity of 2 because of the power. And we'll talk about that later. But just to kind of give you a little heads up. All right, so now we're going to solve for this one. So we subtract 3 and then divide by 2. So x is negative 3/2. So our x-intercepts are 2, 0, and negative 3/2, 0, or 1.5. All right, let me type this in Desmos and show you. Okay, so I went to Desmos and typed in the function, and you can see that the x-intercept is negative 1.5, which same thing as 3/2, negative 3/2, and then 2, 0. And then the y-intercept is 12. I believe that's what we got. 0, 12, I mean. Yeah, okay. And then just to kind of give you, a little precursor of what we're going to do, notice that at 2, 0, again, that turning point is on the x-axis, and it had a multiplicity of 2. We'll talk about that more later. Okay, let's move on to the next example. Example 5, finding the x-intercepts of a polynomial function using a graph. So if I give you the graph, or if you go to Desmos and type this in, you can see what the x-intercepts are. So let's do that. Okay, so I typed in the function into Desmos, and then I can just click on it and it'll tell me what the x-intercepts So obviously that's a nice, easy way to do it. So remember, the x-intercepts, if we work backwards, the x-intercepts will tell us that x plus 3 is a factor, x minus 2, I'm sorry, you changed sign, x plus 2 is a factor, and then x minus 1 is a factor. So if I wanted to factor this, basically you just change those signs. It'll be x minus a minus 3, so it'll be x plus 3, x minus a minus 2, so it'll be x plus 2, and then x minus 1. Okay? So that's a nice little trick there. So let's see. So our x-intercepts are x-intercepts. Let's see, what was it? Negative 2, 0. My graph went away. Negative 2, 0, negative 3, 0, 1, 0. Negative 2, 0, negative 3, 0, and 1, 0. And what I was saying earlier is if I wanted to factor this, these will give me the factors. So it would be x plus 2, x plus 3, and x minus 1. And if you multiply that out, you'll see that you get this polynomial. So I do that as a little challenge to see if you in fact get this polynomial. Okay, on to the next learning objective. Identify zeros and their multiplicities. Identifying zeros and their multiplicities. Graphs behave differently at various x-intercepts. Sometimes the graph will cross over the horizontal axis at an intercept. Other times the graph will touch the horizontal axis and bounce off. So if we have an xy axis, and let's say this is an x-intercept, I could have a graph. As I come down to it, I hit the x-axis, and then I keep going, right? So that will cross it. Sometimes I can have a graph, and then I'm going to approach it, and I have the turning point. I just touch it, then turn around and bounce back. So this will be coming down, hits the x-axis, and then bounce back, right? So that the multiplicity of that x-intercept will tell us the behavior, and we'll get into that. So let me show you on Desmos just a couple examples. Okay, so I typed in a function. I have 3. I factored it for you, or I just typed in 3 factors basically. So this would be if I multiply this out, this would be x to the 3rd power polynomial, and you can see it has 2 turning points, 3 x-intercepts. Now each factor occurs once, so we call those multiplicity. So they all have a multiplicity of 1, and notice at each one of the x-intercepts the graph crosses at the x-intercept. Okay, so now let's look at just one of these. Let's look at the x-intercept 1, 0, which would be the very last one here. So if I make a power, and if I put a 2 there, now look at what happened. It went up, and as I approach it, I hit it, and I have a turning point there. So it's increasing, and then it's coming back down. So it doesn't touch, it doesn't go through, it doesn't cross it, it just bounces off it. So when it intersects, it doesn't continue, it actually bounce, and we'll say bounce. Okay, now again, look at just that one, and watch when I change this to a 3. So not only does it tell you if it's going to cross or bounce, it also kind of gives you the shape. So x to the 3rd has this kind of, for lack of a better term, this S kind of curve, right? So we have this, or snake kind of movement here. However you want to describe that, right? It's a cube function. So if the multiplicity is 3, it's going to behave, if you just zoom in on that spot, it's going to behave like a cube. Now when we do 4, remember 4 is like a parabola but a little flatter, and you can see how it kind of flattened out. So not only does it tell you if it cuts, I say cuts, or goes through and then bounces, it also tells you the shape, right? So if the multiplicity is 1, it cuts through like a line. If it's square, it would bounce like a parabola. 4th, it'd bounce again, but it'd be a little flatter. If it's 6, it'd be even flatter than that, and then steeper, right? So just to kind of show you the difference between that, let me just type this here and then change just that 6 to an 8, and you'll see it kind of, I don't know if you can see that. So the green one, do you see how it's flatter? So if I go back to make that a 2, it's more like a parabola shape. Now if I change that to a 3, oops, well now it's a 1, so it's like a line. If I do it like a 3, it's like a cube shape, right? It has that kind of snake curve. Okay, so the multiplicity for each of the x-intercepts gives you some information about the shape at the or we call it the behavior at the x-intercept. Okay, so it either goes through or it touches it and then bounces off. And then you can go a step further. It also gives you, if you zoom in at that spot, it kind of gives you the shape, x squared, x cubed, x fourth, whatever the case is. Graphical behavior of polynomials at x-intercepts. So to sum up what we were just talking about, if a polynomial contains a factor of the form x minus h to a power, the behavior near the x-intercept h is determined by the power p. We say that x equals h is a 0. So here's the term now. So the x-coordinate of the x-intercept is called the 0 of the polynomial, and it has a multiplicity of whatever that power was in the factored form. The graph of a polynomial function will touch the x-axis at zeros with even multiplicities. So I'll touch it and bounce off. The graph will cross the x-axis at zeros with odd multiplicities. And again, if you want to go a step further, it's going to have the shape of whatever that power is. X squared, x cubed, so on. Okay, the sum of the multiplicities is the degree of the polynomial. So if you have 3 factors and they all have a multiplicity of 1, 1 plus 1 plus 1 would be 3. Let's see if we can go back. So see, we had in this factored form, all 3 of these are power multiplicity 1. So this would be a degree 3 polynomial. And then the one that I did here, so the one that's the green one, this would be 3, 1, 1. So 1 plus 1 plus 3, that would be degree 5. And let me turn the blue one off. And you could see that degree 5, the left end is going down and the right end is going up from what we learned in the previous section. Example 6, identify zeros and their multiplicity. Use the graph of the function of degree 6 in figure 9 to identify the zeros of the function and their possible multiplicities. So all we do is remember the zeros. I guess the book needs to make a distinction too. They don't, but the zeros, there's 2 types of zeros. There's real zeros and there's imaginary zeros. The real zeros are going to be on the equal to the x-coordinate of the x-intercepts. So if we find the x-intercepts, then we know what the real zeros are. So the zeros of the function are x equals negative 3, and it has a multiplicity, it bounces, so that would be multiplicity of 2 or 4 or 6. It's not very steep, so I would say it's 2, but anyway, I'm going to say etc., right? And then this would be x equals -1. And again, it's kind of crossing like a line, so that would suggest that it's multiplicity of 1. But it could be multiplicity 3. And then this one, do you see how that's kind of like a degree 3? It could be degree 5 also, but so x equals 4. Again, it's most likely degree 3. I mean, it's possible that it's a degree 5, right? And then this is most likely 2, but again, there could be some weird things going on, but most likely it's 2. It could be 4, it could be 6, so on. Very unlikely though, just looking at the shape. Our next learning objective, determine end behavior. All right, so we covered this in the last section, if you recall. So basically, if we have a function, polynomial function, a sub n x to the n plus ... Okay, I'm not going to fill in all the terms, but we just care about the leading term. So if the degree is even, the ends will, and the leading coefficient's positive, right? So positive leading coefficient, degree is even, then the left end and the right end both go up. If the leading coefficient's negative, both ends go down. Okay, and then if the leading coefficient's odd, remember I say I think of x cubed, so the right end goes up, left end goes down, provided the leading coefficient's positive and the degree is odd. The degree is odd and you have a negative leading coefficient, then it flips around. The left end goes up, right end goes down. Okay, our next learning objective, understand the relationship between degree and turning points. So in addition to the end behavior, recall that we can analyze a polynomial function's local behavior. It may have a turning point where the graph changes from increasing to decreasing, rising to falling, or decreasing to increasing. That's falling to rising. Look at the graph of the polynomial function. F of x is x to the 4th minus x cubed minus 4x squared plus 4x in figure 12. The graph has 3 turning points. So you can see right here, it's decreasing, it stops, turns, increases. Right, here's another turning point. So increasing, it turns and starts decreasing. Here's another turning point. Now the graph is increasing. So it's decreasing to increasing. This function is, this function f is a 4th degree polynomial. It has 3 turning points. Remember that was one of our ideas in the previous section. It can have up to 1 less than the degree. So if it's 4th degree, it can have up to 3 turning points. The maximum number of points, turning points, is always 1 less than the degree of the function, right? That's just what I said. And again, a turning point is a point of the graph where the graph changes from increasing, decreasing, or decreasing to increasing. A polynomial degree n will have at most n minus 1 turning points, right? So that should be review. Example 7, find the maximum number of turning points for each polynomial. Okay, so a degree is equal to 3. So that tells me that 3 minus 1 is 2 maximum. So maximum of 2 turning points. So you can have up to 2 turning points. This is, now remember, if you were to multiply this out, this is a multiplicity of 2, this one's a multiplicity, we got to be careful, we got x squared here, so we got 2, 3, 4, so this is degree 4, right? Because if you multiply this out, you get x squared plus some other terms, and then you take that x squared and multiply it into this one, you get x to the 4th. So we can have up to 4 minus 1, which is 3. So we can have a maximum of 3 turning points. Doesn't mean we will have 3 turning points, but we can have up to 3, no more than 3. Okay, now to our next learning objective, graph polynomial functions. How to, given a polynomial function, sketch the graph. So your first step, you want to find intercepts, find the x-intercepts, the y-intercepts. Check for symmetry. If the function is an even function, its graph is symmetric about the y-axis. Here's the check. If you plug in negative x into the function and simplify it, and you end up with the original function, that's an even function. If it's an odd function, then it's symmetrical about the origin. That is, and again, this is the check. If you put in negative x into the function and you simplify it, you get the opposite of f of x. Then that tells you it's symmetrical about the origin. Okay, step 3, use the multiplicity of zeros to determine the behavior of the polynomial at the x-intercepts. Determine the end behavior by examining the leading term. Use the end behavior and the behavior of the x-intercepts to sketch the graph. Ensure the number of turning points does not exceed 1 less than the degree of the polynomial. And then optionally, use technology to check the graph. Example 8, sketching the graph polynomial function. Sketch a graph of f of x equals negative 2 times the quantity x plus 3 squared times the quantity x minus 5. Okay, so first we want to find the x-intercepts, or x and y-intercepts. So let's start with the easy one, y-intercepts. Well, I guess if it's factored, the x-intercepts would be easier. So remember that y-intercept, you're putting in 0 for the x and solving it for y. So f of 0 is equal to negative 2, 0 plus 3 squared, x minus 5, oops, that should be 0. So we get negative 2 times 9 times negative 5, which is 90. So we get 0, 90. Our x-intercepts, we're going to set the y equals 0 and solve it for x. So we have to factor it, which already is. So that's nice. Cuts out at work. Negative 2 can never equal 0. So basically you throw that one away. So if there's no x out there, then it's not going to give you a x-intercept. You just basically throw it away. X plus 3 squared equals 0, or x minus 5 equals 0. So remember the 2 is going to go away. We square root both sides. X plus 3 equals 0. And then you're going to subtract 3. But we want to note this has a multiplicity of 2. So we're going to, at x equals negative 3, we're going to get the parabola shape, whether it's coming from the bottom. It's going to be one of these two. Okay? And then x equals 5. So we got negative 3, 0, and 5, 0. Okay, so those are our intercepts. Now we're going to check for symmetry. So if we put in negative x in here and square it are we going to end up with, well, first of all, if we had symmetry about the y-axis, these two numbers would be on the even, would be the same, right? It'd be negative 3, 0, positive 3, 0. So I know it's not even. If I put in negative x, am I going to get odd? So we would have to spin it around. And again, it's not going to work because if I switch these two, if I switch the signs of both of these, I would have to get negative 5, negative 0. So it's not going to be symmetric about the origin. So it doesn't have any symmetry. So I'm not actually going to do the actual test. I'm going to cheat a little bit on that one. Use multiplicities of zeros to determine the behavior. Okay, we already talked about it. So this is multiplicity 1. So that's going to either cut through like that or that way, degree 1. So this one's 2, so it's going to bounce. This one's going to cut. All right, so keep that in mind. Determine the end behavior by examining the leading term. So the leading term is now we have to multiply this out. You don't have to multiply it all out. You're going to multiply the anything that's outside the parentheses with the x to the power for the multiplicity, and then x to the first. And that's going to be my leading term. So it'll be negative 2 times x squared times x to the first, which is negative 2x cubed. So the leading term is odd with a negative leading coefficient. So odd degree, and a sub, in this case is 3, is less than 0. So the left end's going down and the right, oh no, it flips over. So let me fix that. So the left end's going up and then the right end is going down. Okay, so that's my end behavior. And then ensure the number of turning points does not exceed 1 less than the degree. So if it was degree 3, we can have 2 turning points. And so we can do a rough, this will give us a rough sketch. If we want to make it a little bit better, we would make an XY table and pick numbers for X, plug them in, figure out the Y, and plot it, right? We can do a few of those. And then when you take calculus, you'll learn how to find what those turning points actually are. So we'll leave that for another class. But then the idea, if we're just going to do a rough sketch, let's see, we have x is negative 3. Actually, you know what? Let me make this a tiny bit nice. Well, that's fine. Negative 3. And then we got 5. And then 0, 90. Okay, so we'll have to scale this crazy. I'm not going to scale it. I'm just going to say, okay, that's 90. 0, 90. And let's see. Now, for the end behavior, right, you go to the furthest x-intercept on the left, and you know the end behavior is this one's going up, the left end. And then at x equals negative 3, it's a multiplicity of 2. So this is going to bounce kind of like a parabola. And it's going to go through x equals 90. Now there may be a turning point in here too. It may do some things, but again, we would need calculus to figure that out. So another technique, you can put in 1, negative 2 into this function, and you can get this curve just a little bit better. Okay, so somewhere it's going to go up here and top out and turn, and then so I'm just going to draw it like this. It should be smooth. My hand hit a bump on my board here. And then this one, multiplicity, is 1, so it kind of cuts through like a line. And that's pretty much, that's the basic shape. Now let's go to Desmos and see, you know, again, my scale is off a little bit, so if I were to zoom in or change scale, basically we're going to have the two humps, the two turning points. It's going to hit the x-intercept at x equals -3, and the y is 0, and then 5, 0. Okay, so I put in Desmos, and again, you can kind of see, for the most part, it doesn't look exactly like the way I did it, but the same idea. We got the left ends going up. Let me change the y-axis. Hang on. Actually, I changed the x-axis so we can kind of see what's going on. Okay, so you can see that it crosses at -3, 0, bounces, and then it, again, if I had calculus, I could figure out that point. The y-intercept 0, 90. So we pretty much have the pertinent details, see up there? Right, so again, I would have to have calculus to figure out this point right here. And again, that would be for another class. So we got the x-intercept, 2 of them, the y-intercept, and again, we would have to use calculus to figure out this point, or we can estimate it just by picking numbers, plugging it into the function, figuring out the y-coordinate, and plotting it, right, until we find that turning point, which is kind of tedious. So hopefully if you go on calculus, you'll learn how to figure out those relative mins and maxes, those turning points. All right, and then the last learning objective, use the Intermediate Value Theorem. Okay, the Intermediate Value Theorem. Let f be a polynomial function. The Intermediate Value Theorem states that if f of a and f of b have opposite signs, meaning one's positive, one's negative, or vice versa, okay, then there exists at least one value c between a and b for which f of c is equal to 0. I call this the high-low game, right? So the idea then is, remember, a and b are input values. Those are your x values. So if let's say here's a and here's b, and f of a, one of them's positive. So let's say this is f of a. So if we're on the y-axis, this would be f of a, which would be positive, and this would be f of b, which would be negative. So the y value is negative. And since polynomials are what we've talked about it being smooth, continuous curves, the only way that you can have these 2 points on the function, when you draw it, you can't pick up your pencil, so you're guaranteed to go through the x-axis. So somewhere there's a c such that f of c has to be equal to 0. So what you can do is use this technique to kind of hone in on it. So you plug in a, and let's say you get 5, right? So let's say that's 5. And then you plug in b, and let's say that gets you -3. So then you're going to pick a number that's somewhere in between it. Say, let's say you pick this number here, and you plug it in, and you get 2. So, well, that's 2, and that's -3, so it has to be between this choice and that choice. So then you say, okay, let's pick a point maybe here. And then you see that one is below, and now you know it's in between these two numbers. So then you pick something in between, and you just keep kind of honing in onto it until you get the 0, until you find it, or you get close enough, depending on what that is. Okay, so again, I consider it like the high-low game. And you know, if I said, hey, pick a number between 1 and 100, and I'm thinking of a number in my head, and then you say 30, and I say a higher, and then you say 70, and I say lower, and then you say 50, and I say higher. And then, so if the number that I picked in my head was 66, then you would say, okay, 60, and then I would say higher, then it's between 60 and 70, then you'd say 65, and I'd say higher, then you'd say 66, and yep, that's it. Okay, so it's kind of that idea. So you got to pick numbers. If you find one that's above, one that's below, then you know for sure the zero is somewhere in between those two guesses. Okay, so then you're going to guess a number in between there and see what it is. All right, so let's see if we can try it using this technique. Okay, so using the intermediate value theorem, show that the function f of x equals x to the third minus 5x squared plus 3x plus 6 has at least two real zeros between x equals 1 and x equals 4. Okay, so let's make it xy table here, or f of x. Remember, that's y. So if I put in 1 into the function, f of 1 is equal to 1 cubed minus 5 times 1 squared plus 3 plus 6 will be 1 minus 5 plus 3. I forgot the times 1, but it's still 3 plus 6. So 9, 10 minus 5 is minus 5. Oops, did I say minus 5? It's 10 minus 5 is positive 5. So 1, 5. Oops, let me hang on. Okay, so 1, 5. So you see that function's above the x-axis. Right, now we're going to do 4. So f of 4 will be 4 cubed minus 5 times 4 squared plus 3 times 4 plus 6. So we get 64 minus 16, 5. Is that 80 or 90? 80. Plus 12 plus 6, so 76, 82 minus 80 is 2. So 4 is 2. Now, the thing is, right, we can connect these without crossing the x-axis. So, but they told us that there's 2. Actually, let me just do that. So let's try f of 2 now. So if we do f of 2, now save time, I'm just going to do it in Desmos. So let's see, f of 2 would be 0. Oh, I got lucky on that one. So f of 2 is 0. Right, so if I plug it in there, you get 0. So there's 1. So now let's try 3. And again, I'll just plug it into Desmos so I don't have to do all that hard work. And that's going to get me negative 3. So if I plug it in there, so at 3 I get negative 3. Oops, that's not negative 3, negative 3. So now, so basically I know that this is going to kind of touch, and I don't know if that's the bottom, but somewhere down here is the bottom, and then it's going to come up and it has to go through there. The bottom actually might be on this side, but still it's a smooth continuous graph, so I have to, by the intermediate value theorem, there's one more 0 between 3 and 4. And if I wanted to hone in on it, okay, I'm not going to do it, but that pretty much proves that there is. I just cite the intermediate value theorem. So we found that we have 1, 0 at 2, and then because this one's negative and this one's positive, by the intermediate value theorem, there's one more 0, at least one more 0, between 3 and 4. Okay, so let me just show you on Desmos. So let me copy this and paste. Actually, you know what I should do? Oh well, never mind. Okay, so you see how this one's positive, negative, and this one's positive? Actually, yeah, let me do this. X, comma, f of x I guess it doesn't like that. I guess I could do 3. Never mind. I know what I would want to do, but just that's fine. Don't worry about it. So do you see how this one's negative? This one's positive. So somewhere between 3 and 4. So let's try 3.5. So this is basically the game, the high-low game you would play. See? And this one's negative, this one's positive. So it's in between these two. So let's do 3.7. 3.7. Okay, and that's still negative, but we're getting closer. So let's go to 3.8. And this one's positive, so it's somewhere between 3.8 and 3.7. So what about 3.75? Okay, so it's somewhere between those two. So how about 3.76? Okay, that's too small. 3.77. 3.78. 3.79. Still too small. So it's between 3.79 and 3.8. So let's go 3.795. See, that's above. So then I'm going to try 4. So I can play this high-low game to kind of hone in on it. All right, so now let me just show you. So we have the 2, and then it's actually 3.79129. So I was going to hone in on that. Hopefully, yeah, 3.97, that's too big. So I would have gone to 1 next. See, that one's negative, that one's positive. So it's somewhere in between. And I would have to go out a couple more places to get even closer. But again, that's pretty close, right? 3.79, depending on what I'm doing, 3.79 is close enough. Writing formulas for polynomial functions. Factored form of polynomials. If a polynomial of degree n that can be factored into strictly linear factors has horizontal intercepts at x equals x sub 1, x sub 2, ... up to x sub n, then the polynomial can be written in factored form. And basically you're just going to do some coefficient a times x minus x sub 1 to power 1, x minus x sub 2 power 2, so on up to x minus x sub n to power sub n, where p sub I on each factor can be determined by the behavior of the graph at the corresponding intercepts. Right, so that the multiplicity basically, and the stretch factor a can be determined given a value of the function other than the x-intercept. So you need one other point that's not in the x-intercept to figure out a. Okay, how to. Given a graph of a polynomial function, write a formula for the function. So your first step, you want to identify the x-intercepts, find the factors to find the factors of the polynomial. Examine the behavior of the graph at the x-intercept, determine the multiplicity of each factor. 3. Find the polynomial of least degree containing all the factors found in the previous step. And then 4, use any other point on the graph. The y-intercept may be the easiest to determine the stretch factor. All right, let's try this. Okay, so writing a formula for a polynomial function from the graph. So write a formula for the polynomial function shown in figure 19. All right, so our first step was find the x-intercepts. Right? So let's see, we have -3, 0, 2, 0, and 5, 0. So our polynomial for our function is going to be ax minus a -3, so that becomes +3, to some power, which will be the multiplicity, x minus 2 for the next one to some power, so we'll call P1 P2, and then x minus 5 to some power for that one. So now let's so those are our factors. Now we're going to look at the behavior of the graph at the x-intercept to determine the multiplicity, so we know what those powers are. So that's cutting. It goes through like a line, so that's multiplicity 1. And I'm not going to write 1, but 1. And then x minus 2, that looks like a parabola, so we're going to make that a square. And then that looks like a line, so that's going to be 1 again. So it looks like a 4th degree polynomial. Look, 1, 2, 3 turning. So yeah, 4th degree. If we had another turning, we would have to add another degree, and so we might have got our multiplicity wrong. So that kind of jives with what we have. Let's see, now we have this x-intercept, or y-intercept, sorry, 0, negative 2. So if I put in 0, f of 0 is going to be negative 2. And then I can figure out what a is. So we're putting in 0 for x, and then that will get us the y coordinate would be negative 2. And then we just solve this. So we get negative 2 equals a times 3. Negative 2 squared is 4. And then negative 5. So that's 1260, negative 60a. And then we're going to divide by negative 60. So a is 1/30. All right, now we can write our function in factored form. F of, oops, not f of a, f of x. F of x is equal to a, which is 1/30, 1 over 30, x plus 3 to the first power, x minus 2 to the second power, x minus 5. And then that's it. That's our final answer there. And if I go to Desmos and type that in, it should look something similar to this. Okay, and yeah, you can see that it looks pretty similar to what we have there. Right? If I scale it the same. All right, and is that the end of the section? Hang on. Nope, one more thing. So we got using local and global extrema. So local and global extrema. A local maximum or local minimum at x equals a, sometimes called relative maximum or minimum, respectively, is the output at the highest point or lowest point on the graph in an open interval around x equals a. So you're just looking at a portion of the graph. So I zoom in and just look at where I'm circling here. Here, so I'm just looking at a portion of the graph, like right here, and I can see that between, say, this spot and this spot, that's going to give me a maximum for all the x values in between those two, between a and b, is usually what we say. All right, so if a function has a local maximum a, then f of a is greater than or equal to f of x for all x in that open interval around x equals a. If a function, not a as in this a, if a function has a local minimum at a, then f of a is less than f of x for all x in that open interval around a. So again, if I just look at a portion of the graph, say between 3 and 4, we can see that this value is going to be the smallest y value in that open interval between those 2 points. A global maximum, global minimum is the output at the highest or lowest point for the whole entire function. So this is a local maximum, but because it's the highest value for the whole function itself, since the left end and the right end are going down, and then there's no other point higher than this, this would be a global maximum. And then this function does not have a global minimum because it goes down without bound on both sides here. Example 11, using local extrema to solve application. An open top box is to be constructed by cutting squares from each corner of a 14 centimeter by 20 centimeter sheet of plastic and then folding up the sides. Find the size of the squares that should be cut out to maximize the volume of the enclosed box. Alright, so if we start out with a sheet of plastic like this, and then we take and cut out the corners here like that. And then what we can do is we're going to fold up the sides to make a box. So we're going to fold on those dotted lines. Let's see. Find the size square. So they square, that's the key word. So if this is x, this is x, 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 x. We started out with 14 by 20. So this is 20. This is 14. So when we cut out those corners, our box is going to be basically like this. And then that x, that's going to be the height. Okay, so we're going to fold these up. So this would be x, and then this would be this length from here. If it's 20 minus the x minus x, this is going to be 20 minus 2x. And then this length is going to be this piece here, so it'll be 14. I'll write it here, 14 minus 2x. So our volume as a function of x is going to be length times width times height, or depth, however you want to say it, be x, 20 minus 2x, and 14 minus 2x. And let's see here, I can factor out 2 from this one and 2 from that one. So I'm going to get 4x. I factored out 2, so that'd be 10 minus x. I factored out 2, that'd be 7 minus x. Okay, this is a polynomial degree 3, and I want to maximize it. So, and the leading coefficient. Oh, actually, if we were to multiply that out, it'd be 4x squared negative, and then negative make it positive. So the leading term is 4x to the third. So it's going to do something like this. And we'll have up to 2 turning points. Okay. And then is there going to be a find the size square that we cut to maximize the volume? Let's see here. Okay, so I'm going to go to Desmos and plug this in and graph it. But one thing to notice too is what's the biggest x can be. Basically, the biggest x can be is only going halfway, right? So if this was 7 here and 7 here, so x has to be between 0 and 7. So I'm going to zoom in on my x. I'm going to make my x go from 0 to 7 and then see, you know, I'm thinking about here, maybe the graph goes here and I'll have a local minimum, but for the problem that will be the maximum value because x has to be between 0 and 7 for the parameters of this problem. Okay, so let's look at Desmos. And again, I'm going to, let me change my grid. I want to be able to see that top. There it is. And let me zoom in, change my x-axis to be from 0 to 7. Oops, what did I write? T, 7. Okay. And you can see that that portion of the graph from 0 to 7 has a maximum at about 2.7, and it's 339 for the volume. So our max value would be, to cut that square, 2.7, were these inches or centimeters? Centimeters. 2.7 centimeters on each side. So we're going to say x has to equal 2.7 centimeters. So even though it wasn't a global maximum, because of the restrictions that x had to be between 0 and 7, so if we looked at just that portion, you can see on that open, well, in this case it was closed interval, but if you think of the open interval from 0 to 7, we have that local minimum or maximum, which the x coordinate would be 2.7. All right, that brings us to the end of the section, so hopefully that made sense to you. Again, you want to practice, so go to the exercise set at the end of the section, do all the odds or as many as you can, and if you feel up to it, do a few of the evens too. All right, I will see you next time. Have a nice day.